This is the Phillies Emergency Teaching Network. I'm dictating the class lecture from home because there's a snowstorm and there is no way to get in. In fact, I spent 2 hours this morning digging out my driveway. So what you're going to hear is what we might have done in class today if there had been a class. Our first question is on vector manipulations. I should emphasize that the topics covered on the exam will probably vary from year to year, and therefore the fact that this time we are getting a vector question does not mean you will get a vector question when you see the exam on Wednesday. Nonetheless, you're given 3 vectors, A, B, and C, and you're invited to calculate their sum, their difference, their dot product, their cross product, and the z component of the sum of 4 vectors. Finally, there's a trick question. After the displacement, where is the object with respect to the origin? The answer to the trick question is that it's impossible to tell where the object is with respect to the origin because, this is not meant as rocket science, because you know where the change from the starting position to the end position, that's 2a plus b minus c, but you have no idea where you started. Part A of the question is to add the 2 vectors a and b. So a plus b is going to be minus 2 plus 4i hat plus 3j hat plus a minus 4 minus 6k hat. And when you combine the numbers, you get 2i hat plus 3j hat minus 10k hat. Remember, vector addition proceeds by component-wise, so that, for example, the x component of a plus b is the sum of the x components of a and b. You're then asked specifically, question B, what is the y component of a plus b? And the answer is that the y component a plus b is 3. That's 3, not 3j hat. The j hat is not part of the component. So the correct answer is that a plus b y component is 3. If we do the subtraction, we again do the subtraction component-wise. So a vector minus c vector is the difference of the x components, minus 2 minus 1. Separately, the difference of the y components, 3 minus 6. And finally, the difference of the z components, minus 4 minus 0. The net result is that the difference vector is minus 3i hat plus minus 3j hat minus 4k hat. Let's advance to look at the other manipulations you were asked to do. You were asked to do the dot product. You obtain the dot product by multiplying together the components. The x components of the 2 vectors are minus 2 and 4. The y components are 3 and 0. And the z components are minus 4 minus 6. Total all of the numbers up here, and you get minus 8 plus 0 plus 24 is 16. Notice that there are no i's or j's or k's in the multiplication in a dot b, so you don't have I hat, or whatever. You just have 16. We also do the cross product of a and b. In doing the cross product, we apply the rule that a and b are binomials or trinomials. Here's a at the top of the screen, and b is next. A is a trinomial, b is a binomial, and when you multiply them together, you just get the 6 terms, as if you were doing normal polynomial multiplication. So here we have written out the 6 terms, and the first term has a minus 8 I hat cross I hat, and another has a 12 I hat cross k hat, and so on until we've multiplied all 6 terms together. Word of warning: multiplication signs in vector math have very specific meanings, so we only use the X to indicate a vector cross product. If we're doing a dot product, we do an elevated dot. If we're multiplying together scalar numbers, as seen up here at the first line of A dot B, you just put the numbers next to each other. You could use an elevated dot, you could use parentheses. Having written out what A cross B is, we now apply the mnemonic IJK, which tells us, for example, that I cross I is 0. I cross K, how do we get an I cross K? Well, here's an I, there's a K, and I cross K is a J. But we're moving in the minus direction, so I cross K, this I cross K is minus J, and 12 I hat cross K hat becomes minus 12 J hat. We repeat the same process for all 6 terms, and then we can eliminate the 0 and combine terms that are the same, and here is A cross B. Finally, we're asked for the z component of 2a plus b minus c. We get the z component for addition and subtraction simply by adding the components together, and we get minus 4 minus 6 plus 0 is minus 10. That's the displacement, the change in the position of the z coordinate. However, while the displacement is known, we have no idea where we ended up because we don't know the starting point. The displacement vectors just give us the change in the position, not where the object was. And therefore, as we see here, the location is unknown because the start is unknown. Question 2, for 30 points, discusses forces and action forces and reaction forces. You have to draw a force diagram. You have to identify the force, the object on which the force is acting, the physical nature of the force, and the object exerting the force. You then have to identify the reaction forces. And for each reaction force, you have to identify the force, the target of the force, the nature of the force, and the object exerting the force. We're going to be a little bit screen limited in terms of how many words we can fit on the screen, so you are not going to see complete sentences here. Nonetheless, you are going to see the force diagram and the heroine making her perhaps escape. In the upper left, we see a proper force diagram. There are only 2 forces acting on the heroine, namely the force of gravity and the tension in the rope she's hanging on to. Gravity points down, tension points up. X and Z indicate one of actually a very large number of different possible coordinate systems. It is important to emphasize what you do not see in the force diagram. You do not see a V and an arrow pointing horizontally. That would be the mythical force of velocity. You do not see something pointing up or down labeled F sub c, a centripetal force, because there are no such things as centripetal forces in our coordinate system. The only forces acting on the heroine are T and mg. And so on the next 2 lines, we write out that T is the force on the heroine due to the rope's tension, and mg is the force of the Earth's gravity on the heroine. The reaction forces are a minus T, the force on the rope due to the heroine. That's a reaction force to T, the force on the heroine due to the rope. And then a minus mg, the force on the Earth due to the heroine's gravity, which is the reaction force to the force of the Earth's gravity on the heroine. Notice, that is important, that the T and mg on the heroine are not an action-reaction pair. Yes, there is a T force on the heroine, there is an mg force on the heroine, but those two forces are not an action-reaction pair. The two forces in an action-reaction pair must be on two different objects. Question 3 deals with motion at constant acceleration. We have an object that's moving, we're at constant acceleration, we're given certain pieces of information about it, and we're asked to write, for example, position versus time in a fixed form, namely the fixed form given here. The rocket problem describes motion at constant acceleration. The top line is the general equation for position versus time for motion at constant acceleration. The acceleration has to be constant. And we're given three pieces of information, namely the altitudes at times 1, 2, and 4. The altitudes at those three times are 91, 84, and 76, and therefore we can write position versus time at those three times by plugging correctly into this equation. The altitudes are z, which is some function of time, and we replace time with its three values, namely 1, 2, and 4. So we now have three equations into three unknowns. The three unknowns are the constants of integration z0 and v0z, and the vertical acceleration a sub z. How do we solve these equations? There is one and only one highly efficient procedure for solution, and that highly efficient procedure for solution is subtraction. We take, for example, the top equation and subtract it from the second and third equation. What's the point of saying subtraction? We take the equation that we are subtracting and we multiply it by some constant, in this case 1. So when we do the subtraction, we cancel out one of the unknowns from the two remaining equations. So in this case, we would like to have z0 minus z0, which is 0. So we multiply the first equation by 1 and subtract it from the second and third equation. When we do that, we have, for example, 84 minus 91 is minus 7. 76 minus 91 is minus 15. That's the left side of the equation. The z-naughts cancel out because we subtracted them. And the remaining coefficients of v0z and az are determined by subtracting the two equations. We would now like to proceed to the next line. We now have two equations in two unknowns. Our next step is to subtract. We might as well use the top equation and subtract it from the second equation after some constant multiplication. And if we do that properly, we eliminate v0z. So we notice that in the first equation, v0z is multiplied by 1. In the second equation, it's multiplied by 3. And therefore, we subtract 3 times the first equation from the second, and we get minus 15 is equal to minus 3 times minus 7. You see, here's the subtraction. And we have a v0z, which is times 3. And we multiply it by 3 times the first line, and the v0z's cancel. And we are left with az and nothing else multiplied by some numbers. We now take the bottom line and we simplify it, clean it up, and a little division gives us that a sub z is equal to, in this case, plus 2. Now that we have a sub z, we can plug it in to one of the equations up here and compute v0z. That gives us v0z, and we work back up to the top. We now know v0z and az, and we plug it in, and we can solve for z0. Having done this, we can write z in terms of the three unknowns z0, v0z, and az. So that's how we proceed with this. You notice that at the end of my discussion of Roman 3, I didn't actually solve for z of t. I left that for you to do. I'm showing you how to solve the problem, not exactly what all the numbers are. We finally advanced to Roman numeral 4 and the bonus questions. Roman numeral 4, we have a new and improved rocket car whose engine delivers a horizontal force that increases quadratically with time. The rocket car with engine has mass m. It's on horizontal ground. Find the force diagram, the acceleration, velocity, and the position as a functions of time. You're also asked, assuming that the length of rope between the pivot point and the heroine's hands is 20 meters, at the bottom of the swing the heroine is traveling at 15 meters per second, and the heroine with body armor and other equipment masses 70 kilograms, find the tension in the rope. And second bonus question, what was my advice in the course syllabus about memorization? Well, that one's very easy if you read the course syllabus, and is a little more challenging if you haven't. We now reach the solution to problem 4. We have an object moving under the influence of external forces. Our first step is therefore always to draw the force diagram, which we see in the upper left of the figure. The indicated forces are a normal force due to the ground, mg, the force of the Earth's gravity, and an F0 t square I hat, the force due to the rocket engine. In order for this to be a correct force diagram, we have to show coordinates, and I've put in an x and a z in the reasonable way. Our next step is to insert the forces into the second law. So I actually write out the second law itself, m d square r dt square equals f, and then I note that the only interesting component of the motion here is in the x direction. We are on flat horizontal ground, the car stays on the ground, so n and mg must be canceling so that the z acceleration is 0. Our second line is then m d square x dt square equals f0 t square. Notice that in the first equation, both sides of the equation are vectors. In the second equation, both sides of the equation are scalars. I'm applying the Curie principle that a vector is equal to a vector, a scalar is equal to a scalar, but if you write vector equals scalar, you can be absolutely positive the equation is wrong, even if you have no idea whatsoever what the equation means. In order to advance, we integrate both sides of the equation with respect to time. That's indicated on the third line. Observe that there's an integral sign and a dt. You must have the dt there to indicate with respect to what variable you are integrating. If there's no dt, the answer is wrong. Also, if you don't write down the integral dt, you are in some danger of joining former classmates who integrated one side of the equation with respect to t, the other side of the equation with respect to x, and then wondered why the equation was total nonsense. Well, it's dimensionally impossible. The integral dt by itself has a dimensions of time to the first power, and so the integration adds a factor of t to both dimensions on both sides. The net result is that we have a velocity dx dt, and I've done the time integral, and the integral of t squared dt is t cubed over 3, and I've picked up v0x. v0x is the constant of integration. Pushing right ahead, I integrate with respect to time again, and dx dt integrated with respect to time gives me the position x. I integrate the variables with respect to time. That was a t cubed over 3, so it becomes t to the 4 over 12. And I pick up constants of integration as before. Is there a booby trap here, a trap for a boob? Well, yes. We have an equation x equals x naught plus v0x plus 1/2 a t squared, which we used in the last problem. That equation is only true at constant acceleration. Here the acceleration is not constant, so the problem does not arise. Observe also that since the acceleration is a function of time, that's the t to the 4 term, that the average acceleration depends on time, and therefore you can't replace the acceleration d square x dt square with some average acceleration and get a correct answer. A few of you have picked up the peculiar formula v square equals v0 square plus 2ax, or something like that, which appears to arise out of the swamps and needs to be sent back there. The important issue is, well, if you're going to use a formula, you should know under what conditions it applies. And the important answer is that's actually conservation of energy written very strangely, and that formula does not apply unless the acceleration is constant, among other things. Okay, let's push ahead to the bonus problems. And the first bonus problem deals with the heroine swinging on the rope. And so I'm going to actually write out the problem from the start. There are two forces on the heroine, the tension of the rope and the force of gravity. There's only one interesting coordinate, z. And I can therefore write out force as mass times acceleration. So t minus mg is m times d square z dt square. Observe that since we are grown-ups, we use the grown-up symbol for d square z dt square, not the little small children's symbol a. We are swinging at the end of a rope. Well, someone else is. I certainly wouldn't pull this stunt. Well, maybe if there were a pride of lions trying to eat me. And since the rope is simply swinging, this is motion. It's circular motion. At the very bottom of the swing, and no place else, but we are at the very bottom of the swing, and at the very bottom of the swing, our velocity is straight sideways, and momentarily our acceleration is 0. We're moving at constant speed. And since we are moving in a circle at constant speed, we can use the formula v squared over r for circular motion. However, when we do that, we have to do one important thing. We have to remember that v squared over r is the magnitude of the acceleration. In order to get the actual acceleration in there, g, we'd better get a sign. And the answer is we are moving in a circle. We are below the center of the circle. Therefore, the acceleration is up. That's in the plus direction, and that's where this plus sign came from. I rearrange things by moving the mg to the other side, and when I do that, I can stick in numbers. If I stick in numbers, you notice that the tension in the rope is about slightly more than twice mg. Therefore, the heroine to hang on is actually supporting twice her body weight with her wrists. Is this possible? Well, some of you may have seen Olympic gymnasts doing the uneven bars. That's the women's event. If you're doing the uneven bars, don't look at me. At the bottom, if you're really good, you're potentially supporting 4 times your own body weight with your hands. You need really strong grip or you go flying. However, there's the answer. There's the tension. It's, of course, in newtons or something like that. It's newtons. It's a force. Oh, the other question is, what did I say about memorization? I said what's in the syllabus. Maybe you should read the syllabus.